Okay, I think everyone knows you, but we're pleased to have Payman Eskandari, who still says he's from the Fields Institute, which is good, but he's also from University of Winnipeg.
No, I meant the talk was at the Fields Institute, but
And he's speaking about Grothendieck period conjecture and mixed models with maximal unipotent radicals. Yeah, go ahead.
thanks, Kumar. So I'm going to start with some motivation and background. So we all know the Riemann zeta function, defined that way. And before it was called the Riemann zeta function, Euler proved that some very nice statements about its special values. So zeta of 2, 4, 6, and as a matter of fact, all at positive even integers. They have this very nice behavior that up to a rational number, zeta of 2k is pi to the power of 2k. And around the same time as Euler, Lambert proved that pi is irrational, and then later on, Lindemann proved that pi is transcendental. And now, combining these, what follows is that zeta of 2k for every k is actually a transcendental number. Now, as we all know, the behavior for odd values is very, very different. So Euler already observed that. So he played a lot, with odd zeta values as well. And he gave up on, zeta of 3 being pi to the power of 3. He thought that that's probably false, but he formulated some other conjecture that maybe zeta of 3 and log of 2 and pi satisfy such a relation with coefficients in Q. To date, still very little is known about values at odd numbers, values of the zeta function at odd numbers. The only thing that is known about a single odd zeta value is this fascinating theorem of Apéry that zeta of 3 is irrational. We don't know even irrationality of zeta of 5, and nothing is known about transcendental of any odd zeta values. There are some statements about, from this set of zeta values, odd zeta values, at least this many of them, would be irrational, things like that. But about anything definitive about a single zeta value, this theorem of Apéry is the only thing. The likely expectation in modern times is that pi, odd zeta values, and values of logarithm at primes, all these numbers should be algebraically independent. And this likely expectation it's a prediction of Grothendieck's period conjecture, which I'll be speaking a lot more about this. So on routes to Grothendieck period conjecture, let me start with a little bit of background here. So if you take an algebraic variety, there's different cohomology theories for that. There's the Betti or singular cohomology theory, there's the de Rham cohomology theory, there's the lattice cohomology theories, and so on and so forth. Now, these two, Betti and de Rham, you have the integration pairing between them, and that leads to periods. Now, Grothendieck had this dream, so some people call this Grothendieck's dream, that there should be something in between. So, if you think about this process as some sort of linearization, so you're associating these linear spaces, these vector spaces to a variety, Grothendieck's vision was that, you should be able to do the linearization on the algebraic geometry side, actually. So there should be some, theory of motives that, it's truly algebra geometric, but, still does the linearization, which is to say that, you'll get a category that's Tannakian. I'll say more about this, but, it satisfies similar properties to categories of vector spaces, but it's in the algebra geometric side. And then from there, you have these realization functors that take you to different cohomology theories. Now, a lot of people have worked on this, theory of motives, Grothendieck himself. Actually, the idea sort of, and there's a prehistory for it too, that goes back to Serre, those compatible systems of elliptic realization, elliptic representations. That's got a prehistory, and then really on working on motives, Grothendieck himself, of course, and then there's many others, including Delin, Janssen, André, more recently Voevodsky, and then, much more recently as Ayub and Nouri. Many, many people. I'm missing a lot of names, obviously, but These people have made very significant contributions. Now, nowadays, after decades of work of many, many people, we actually do have non-conjectural geometrically constructed categories of motives. Now, there's two constructions. One is due to Ayub and one is due to Nori. And these are actually known now to be equivalent to each other. Now, of course, when I say non-conjectural, the constructions are non-conjectural. So you do get, Tannakian categories. I'll say more about this in a second. But there's a lot of it that still is conjectural. You expect that category of motives, extensions in the category of motives should be related to, higher Chow groups, and, they should be related to K theory, and those things are all still conjectural. But at least you do have a, geometric category to work. Now, this Tannakian, what does that mean? That means that, this is just a reminder, I know everyone here is familiar, but I prepared the talk with a little broader audience in mind. So this means that there's a category has similar properties to categories of representations. So it's an abelian category, there's a tensor product, there are duals, and these are nice duals in the sense that double dual of every object is the same as the object, canonical isomorphic to the object, and admits a fiber functor, which, in setting of representations, that would be, the forgetful fiber functor, for example. Key fact about Tannakian categories is that, by the way, here I've just written representation, and I keep just saying representation, but I mean finite dimensional. The key fact about Tannakian categories is that, any Tannakian category over a field of characteristics 0 is equivalent to the category of representations of some affine group scheme over that field. More precisely, if you have a Tannakian category T over K, and if you choose a fiber functor from T to vector spaces over K, now when you look at the automorphisms of the fiber functor, that is actually an affine group scheme, and the obvious functor that you have from T to the representations of this, because this is automorphism. So, by definition, this acts on omega of every object. So you do have such a functor, and the theorem, the fundamental theorem of Tannakian formalism, is that that's actually an equivalence of categories. Now, this affine group scheme here, I'm going to call it the fundamental group of the category with respect to the fiber functor. And you have an equivalence of categories between representations of that and the category itself. So you can really think of this as the category of representations for many purposes. Now, I'm moving towards stating Grothendieck's periodic conjecture. Before that, I need to make a definition here that if you have a motive X over a subfield of C, the Motivic Galois group of X is by definition the fundamental group of, so you look at the subcategory the Tannakian subcategory generated by X, that's the smallest Tannakian subcategory that contains X, and it's closed under taking subquotients. And then it's the group associated to this category, to the subcategory via Tannakian formalism. It's the fundamental group of this subcategory for the particular choice of fiber functor being the Betti fiber functor. So Betti cohomology. Now this would be an algebraic group over Q, because our category of motives is a Tannakian category over Q. And you can identify it by just looking at the action on the generator X. You can identify it as a subgroup of GL of X. And you have an equivalence of categories between the category generated by X and representations of the Motivic Galois. Now, okay, so for every object, every motive X, I have this Motivic Galois group, and Grothendieck's period conjecture asserts that for every motive X over a number field, the dimension of the Motivic Galois group is equal to the transcendence degree of the field generated by the periods of the motive. Now, this equality here, one little comment that I will make here is that actually, so the fact that the transcendence degree is at most this dimension, that's not difficult to prove. Really, the hard part of this is really the transcendence, statement that this transcendence degree is at least also equal to this dimension. Now this is a Grothendieck period conjecture for number fields. Now there are generalizations of these also for other subfields of C. Now one little comment that I make here, because I think it's really fascinating. Grothendieck actually formulated the conjecture in this language, and which is very fascinating because none of these things, there was no category of motives really at the time, but he really had this vision and he formulated the conjecture in this language. Now, a trivial, in quotation, exam sort of case of this conjecture is the following. So if you look at, if you apply this to H1 of C star, which, this is the Lefschetz motive Q of -1, pure of weight 2, one-dimensional. So this, it's Betti and the Ram realizations are written here. So the Betti realization for the homology is given by, it's generated by the unit circle. And for the Ram, it's generated by dz over z. When you look at the integration pairing, you get 2 pi I. Periods are rational multiples of 2 pi I. And so the Motivic Galois group, okay, so it's a subgroup of GL of the Betti realization. So that's one dimension, so it's a subgroup of GM. And turns out that it has to be equal to it here because it's not a trivial object after all. It would be equal to it. And so now this is one-dimensional. The Motivic Galois group is one-dimensional. Periods are rational multiples of 2 pi I. So here, Grothendieck period conjecture for this motive is, that's equivalent to transcendence of pi, which of course is a theorem. So one little comment here, if I say Grothendieck period conjecture for a motive X, I mean this equality for X. By the way, feel free to interrupt me at any point. I don't see the chat box or anything. Just have the slide in front of me. Okay, so now I want to talk a little bit about unipotent radicals of Motivic Galois groups. Now, category of motives has is filtered as a functorial filtration, weight filtration, has similar properties to the weight filtration on polarizable mixed-Hodge structures. So for any object, any motive X, there's this associated gradient with respect to the weight filtration, and that's a semi-simple object, just like for polarizable mixed-Hodge structures. Now, because the category generated by the associated gradient is contained in the category generated by X, you get a surjection from the Motivic Galois group of X to the Motivic Galois group of the associated gradient. Now, this is a reductive group because that's a semi-simple object. Now, because weight filtration is functorial, this is contained, well, of course, we know that it's contained in GL of X, but because weight filtration is functorial, it will be contained actually in the parabolic subgroup of GL, corresponding to the weight filtration. So the automorphisms that respect the weight filtration. And then you have from this parabolic subgroup, you have a surjection to GL of the associated gradient, and this diagram here commutes. Now, if you look at the kernel of this, so this would be, so, if you're trying to, so if pick, once we take bases and all of that, this would be now, this is, you can think of this as invertible block diagonal matrices. And then this one would be, upper block triangular invertible ones. And then the kernel of this would be the ones that have ones on the diagonal. It's the unipotent radical of this parabolic subgroup. And this would be, and if I define the kernel of this surjection to be U of X, U mod of X, that's contained in here. That's a unipotent group, so that would be unipotent. This is reductive, so this will be the unipotent radical of the Motivic Galois group. Now, if I look at the Lie algebras, the Lie algebra of this will be contained in the Lie algebra of this, which is endomorphisms that, that is W minus 1 part of the endomorphisms. In other words, that this is the endomorphisms that send each Wn to Wn minus 1. They drop the weight by 1. So this is the Lie algebra. This U of X is the Lie algebra of this group, this unipotent radical. It's contained in this W minus 1. And now, because via Tanakian formalism, so you actually get a motive, so denoting by this underlined U of X, which is a submotive of W minus 1 of end of X. This is the internal harm. You get a submotive U of X of that. Canonical submotive here, whose Betty realization is that Lie algebra. And the point is that what you do is that you look at the, you have to use that equivalence of categories. So I'm going to look at the representation of, I'm going to look at the adjoint representation of this, and I'm going to look at this restriction to here. And that's going to give me my motive. And it's contained in, it's compatible with the action of this thing on this guy by conjugation and all of that. So this is where this comes. Okay, so this U of X, this Lie algebra, is contained in this W minus 1 of and X. Now, so we're going to come back to this inclusion later on. So let's keep that in mind. But a couple of comments here that unipotent radicals of Motivic Galois groups have actually been studied quite extensively by many people. I've listed some names here, but the list is not exhaustive. So Deline, Bertrand, Erdogan, Bertolin, Peter Josen, and Kumar, and myself, and others, they have studied this group. Philosophically, and an instance of this philosophy will be, we'll talk about it in a bit, but philosophically, this unipotent radical is related to the extension data in the category. Now, I'm going to move on to and talk about Grothendieck's period conjecture and algebraic independence of odd zeta values and logarithms. Before that, I'm going to remind what's known about X groups in the category of mixed motives between one and these Tate objects. So in other words, these are X groups in categories of mixed Tate motives. Now this Qn is, so we talked about what Q minus 1 was. Q1 is the dual of that. Q1 has weight -2, and then Qn is tensor power of Q1. Now, this sort of puts together works of many people. This is so Borel's beautiful theorem on calculation of K theories, K groups. Sorry, and then there's a work of Wowoski and Levine on mixed Tate motives that they show that they construct a category of mixed Tate motives in the way that the X groups are related to K theory, the way they are expected to be. And also some statements here are also actually due to Soule. Now, the description of X groups in mixed Tate motives is as follows. So mixed Tate motives over Q. So for any n that and being odd and bigger than 1, this X group is one-dimensional. For n being positive and even, this X group is 0. And this description is the same in the category of mixed Tate motives over Z. What does that mean? So this is the full subcategory of mixed Tate motives over Q, consisting of objects that are not ramified at any prime. So you look at the L-adic realization, and there's no ramification. So for n bigger than or equal to 2, these two groups are the same. You notice that n being 1 is excluded from here, and that's why the picture is very different for n equals 1. So extensions of 1 by Q1, mixed Tate motives over Q. These are given by Kummer motives. So there's a canonical isomorphism between this and Q star tensor Q. And under this, A is corresponds to this homology, relative homology, C star, and then 1 comma A. And this is a two-dimensional motive. And when you look at its period matrix, see, because you're looking at the relative homology, now the straight line from 1 to A here becomes becomes actually a co-cycle. It becomes a cycle. So I can now, if I integrate dz over z over that, I'm going to get a log of A. The period matrix looks like this, and that's where this log comes from. Now this motive, I'm going to call it the motive of log of A. I'm going to just denote it by L sub A. And this motive is ramified at A and nowhere else. It's a motive over Z with A inverted. Now, for mixed state motives over Z, well, all of these are ramified somewhere. So mixed state motives over Z, the X group here will be 0. And mixed state motives over Z or over Q, or actually in any of these intermediate categories, the X2 groups always vanish. And this becomes important in later slides. Okay, so now extensions of 1 by Qn and being
Payman, could I ask
yeah.
a question about I wonder whether there's a concept of a potential Tate motive. That is something which becomes a Tate motive over a finite base change. And if we can make sense of that, then what would the X groups be for that? Do we know that?
Yeah, I don't know. I don't know about that. Yeah, I don't know.
You could do that, then you see you can start twisting by characters. Yeah, so I mean that would be the first step beyond Tate motives, maybe.
I think there are Hickey motives. I don't know.
Yeah,
much
there are even Artin motives, but yeah, so I just don't know what implications that has for this kind of thinking, though.
Yeah, for periods. Yeah, that's a good question. I don't know.
Payman, may I ask a question as well?
Yeah, of course.
This theorem that's being proved by like in 72 and 78. So these people don't have any construction of the category of a category of motives, right? So in
That's
what
correct.
language are they? In
Well,
what
that's
language
K
are they
theory. So
proving?
this comes from these are computation of K groups. That's how you get these things, and those computation of K groups are what Borel does. Now, Blavatsky-Levin portion is to relate extensions of, to construct a category of mixed state motives in a way that its X groups are related to K theory.
I see. So
Right?
the theorem
that's in K theory.
is I see.
Borel's working K theory, yeah. So it's
I see.
basically computation of K groups of number fields. That's what Borel does. That's Borel's part in this.
Of number fields or rings of integers, isn't it?
Both.
Yeah, and also Soule, I think, was working on this.
Oh yeah, actually, yes. So yes, so Borel is for rings of integers, and the fact that they are the same, that's Soule. That's work of Soule.
Yeah.
Okay, so now these one-dimensional spaces for n 3, 5, and so on and so forth. So now this is the work of the Lean that shows that the non-trivial extension of 1 by Qn. So first of all, I said the non-trivial extension because of the following, because this X group is one-dimensional in this case. So the middle object actually, if you take any non-trivial extension, the middle object will be isomorphic because of this one-dimensionality. So up to isomorphism, there is actually just one non-trivial, there's only one motive that's a non-trivial extension of 1 by Qn, one mixed state motive over Q. And the Lean proves that it has this period matrix. So there's zeta in here. And I'm going to refer to this motive as the motive of zeta n, and I'm going to denote it by Zn. Now, as a warm-up exercise, so as I said, I want to talk about, and say that, I'm moving towards explaining where, this likely explication comes from, how Grothendieck's period conjecture implies that. So as a warm-up exercise here, I'm just going to discuss algebraic independence of pi and zeta of n, and algebraic independence of pi and log values. So if I take a motive X that sits in a non-split extension like this, and here n actually could be also 1 for the purpose of this slide. Okay, so this would give rise to an extension an extension of algebraic groups like this. So the motivic group of X would surject to the motivic group of the associated graded, which is a copy of GM. And you've got the unipotent radical sitting here. Now, because it's two-dimensional, that previous slide that we had, how this sits inside the unipotent radical of the parabolic subgroup, that unipotent radical here now just becomes this this group, this subgroup of GL2, which is isomorphic to GA, the additive group. So this is contained in here. And now, because X is not semi-simple, because you take a non-split extension, this can't be trivial, because then this would be GM and it would be reductive. So this can't be trivial. It has to be all of GA. So now this is, dimension of this would be 1 from here plus 1, 2. So this has dimension 2. And now the period matrix, so this was for n being, anything. So it could be 1 or, 3, etc., etc. So when you apply this, what you get is that the Grothendieck period conjecture for Zn, motive of zeta of n. Okay, so the Motivic Galois group being two-dimensional, the periods should have transcendence degree 2, so pi and zeta of n must be algebraically independent. And then for LA, you get that pi and log of A should be algebraically independent. So this is what Grothendieck period conjecture for these two-dimensional motives amounts to. Now, moving on to the more general statement.
We do know that pi and log A are independent, right?
Yes, I think so. Actually, do we know that they are algebraically independent, or?
I'm not sure. Pi and log 2, for example. I don't know. I think my guess is that it might be known. It's a good thing.
Yeah. Well, I think that we definitely do know that they're linearly independent over Q bar.
Yeah, that you can get from Baker. Yeah. Because pi is log minus 1.
Exactly. Yeah.
You use Baker's theorem.
Yeah, the algebraic independence, I don't know, but I won't be surprised if it is known. But yeah, I don't know. Okay, so now this more general statement, proposition. By the way, this is not, I'm not presenting this portion as new work. So this is, this is known to people that work with mixed state models. So Grothendieck period conjecture, the proposition is that it implies algebraic independence of this set. So I'm including all odd zeta values, pi, and all log values at primes. So first thing to prove this, let's focus on just algebraic. So, let's not worry about this portion. We'll come back to this. That's actually the more interesting part, algebraic independence of this portion. But let's for now focus on algebraic independence of this set over the field generated by these ones. Now, for that, okay, so let me introduce a notation.
Payman, just to comment on what you just said, that it's well known. It might have been well known to experts, but it's never written in the literature.
As far as I know, I've never seen it anywhere explicitly written either. You're 100% right. I've just
and it's important because there was this question of Euler that was just open for a long time, and so I think it's, after the fact they can say they know it, but
I think so. Yeah. But for algebraic independence of these log values over that field, so let's introduce this notation here. So here we're taking the direct sum of all the motives of zeta values up to some odd number, 2k plus 1 here. And it's enough to show that if you look at the direct sum of this, and okay, so the idea is that you start throwing in motives of logarithms into this. And as long as it's enough to show that if I throw in, so I throw in up to the nth prime, and then I throw in the n plus 1th prime, it's enough to show that the dimension of this Motivic Galois group is less than the dimension of this one. Because then your transcendence degree, when you throw in the next log motive, your transcendence degree would go have to go up, and then so log of Pn plus 1 would have to be algebraically independent to everything else that's been already there. Now, to show this, if you look at the sequence here, so I'm looking at, again, sequences that, by going to the surjections to the Motivic Galois groups of the associated graded. If you look at the sequence here, it's easy to see that it's actually enough to show that the natural surjection from the Motivic Galois group of this one, so here I'm including the n+1 log motive, to excluding the n+1's log motive. This is not an isomorphism. If you show this, that's it. And that's equivalent to showing that motive of log of Pn+1 is not contained in the subcategory generated by this whole thing. So you're including zeta motives up to, a certain point, and then you're including log motives up to for all primes before this. And now this follows from what we know about extensions of mixed state motives, because this one here, okay, so this is ramified at Pn and nowhere else. This whole thing is not ramified at Pn+1, whereas this one is ramified at Pn+1. So this can't be in here. So that portion is follows basically from that description of X groups that we had from before. Now I'm going to focus on the algebraic independence of this part. And for that, again, follows from what we know about X groups, but it's got an extra component here. So same notation as before. This means that the sum of motives of zeta values up to 2k+1. And by similar argument to the previous one, it's enough if you show that the motive of zeta of 2k+1 is not contained in the direct sum in the category generated by the motives of zeta values before 2k+1. And now there's a lemma here from it's actually a group cohomology, comes from group cohomology. I have it written here about extensions in the category of group representations of algebraic groups. So suppose that G is an algebraic group over the field characteristic 0, and it's realized as the semi-direct product of a unipotent group U and a reductive group R. Now let UAB be the abelianization of the Lie algebra of U. Now G acts by the adjoint representation on little u, the Lie algebra of U, and then that descends to action on this abelianization. But and so you consider this as a G representation. One little comment here that it's actually a semi-simple G representation, because the action of U on its own Lie algebra the action of U on this abelianization is trivial, so the action of G on this actually factors through an action of R, which is reductive. So this is actually a semi-simple representation of G. Now, the assertion is that for every semi-simple object N of the category of G representations that doesn't contain a copy of one, you have a canonical isomorphism between extensions in the category of G representations of 1 by N and HOM in the category of G representations of UAB to N. Now, if you apply this result with G being the Motivic Galois group of zeta values up to motives of zeta values up to 2k-1, and you take N to be Q of 2n+1, what you get here, why that equivalence of categories that we have, Tanaka formalism, you get that extensions in the subcategory. So this G becomes a category generated by this object. Extensions in this subcategory of 1 by Q 2n+1 is canonically isomorphic to HOM in the category of motives between this abelianization and Q2n+1. Now, by weight considerations, you easily see that this is actually 0, because this, after all, is a quotient of U of this, and U of this is contained in this W minus 1. And then if you look at, the way the weights are spread out here, the highest weight is, of course, 0, and the lowest weight would be, lowest graded piece would be Q2n-1. And you can't have a Q2n+1. That thing, the weight is too small to be contained in here, too negative to be contained in here. So this is 0. There's no this X group is trivial. So you can't have Z2K plus 1 in here because that's a non-trivial extension. Any question about this argument?
So Payman, perhaps what it comes to the proof of this lemma? Like, is it yeah?
Yeah. So you could prove it, with bare hands. Actually, you could prove it with bare hands. Really writing everything, and it's not ugly. It's a nice proof. I actually, because I didn't know that it was known, so I in a preprint on archive, and like I've written a bare hands proof for this. But you could also get it from group cohomology. So the Hochschild-Serre spectral sequence, basically, you could use that and you get this.
Oh, I see. Oh, okay.
Yeah, for group cohomology for algebraic groups. So now I'm gonna move towards the second part of the title of the talk, which is motives, maximal, unipotent radicals. Now I'm gonna motivate this via what we saw so far. That see, if I wanted to get algebraic independence of pi zeta of 5, so zeta of 3 and log of 5. By the previous argument, what we had to do was to take motive of zeta of 3 and the direct sum of that with motive of log of 5. We use the 4-dimensional motives to get this algebraic independence by assuming Grothendieck spirit conjecture. And associated gradient is this. Now, the question is, well, can you be more efficient and try and do this with a smaller motive? Is there a 3-dimensional motive that has Z3 and L5 as its subquotients? That's my first question. And my second question is that, well, if there is such a motive, would the Grothendieck period conjecture for that motive also imply algebraic independence of these 3 numbers? Now, the first question, this is actually answered by Grothendieck's theory of blended extensions. And I'm gonna talk about this briefly. So Grothendieck invented this theory to study 3-step filtrations in an abelian category. So if you have a 3-step filtration like this, and you've been given 3 objects, A1, A2, A3, and you're looking for such filtrations with a fixed, well, not with a fixed yet, but such that X1 is isomorphic to A1, X2 mod X. So I'm looking at the successive subquotients. They are isomorphic to A1, A2, A3. So he wanted to study these things, such objects, such filtrations. And the observation is that if you give me any 3-step filtration like that, well, that 3-step filtration gives rise to a diagram like this, where the rows and columns are exact. So this is all, by looking at the natural inclusions and natural projections. And then once I choose isomorphism, these 3 isomorphisms, once I choose an isomorphism phi, like that, then I can replace this X1 by A1, this one by A2, and these 2 by A3. And that leads to a diagram that's going to look like this. And that brings us to the definition of a blended extension. So what you do is that you fix 2 extensions, this one and this one. So I'm calling this one script L, this one script N. You're fixing these 2 extensions. That's important. And a blended extension of N, so a blended extension of this extension by this extension, by definition, is a commutative diagram of this form where the rows and columns are all exact. Now, the notation that Grothendieck uses is that he uses capital X-span and L for the collection of all blended extensions of N by L. And then expand just with the little e being capitalized for the isomorphism classes of blended extensions of N by L. So it's a similar, picture as you had for, X and then X groups, right? So you've got the capital X, that's just the collection of all extensions. And then what we write as capital EXT for equivalence classes or isomorphism classes of extensions. Similar thing here. This is the isomorphism classes of blended extensions. What's the notion of isomorphism for two blended extensions of n by L? It's so you want commuting diagrams between commuting maps between the two diagrams in a way, so that's the restriction, that the maps that you get on L and N are identity. That's the key thing. So similar to equivalence of extensions, how you two extensions of A2 by A1, you say that they are isomorphic or equivalent if there's a map between L to the middle object to the middle object, giving commutative diagrams in a way that you have identity here and identity here, right? And similarly here, to go from here to here, your equivalence relation is that you want maps which are identity here and here. And then what he proves is the following, that two results. One, that expand NL is non-empty, so there is a blended extension of n by L, if and only if, when you look at the composition of the two extensions. So this is the Yoneda composition. So that's now, I just go from here. This one is the composition of these two, and I go down. Now this is a two extension of A3 by A1. And the claim is that there exists a blended extension of n by L, if and only if this composition vanishes in the X2 group. So one thing that, the way this is going to appear in the talk is that, as long as, keep this in mind, as long as X2 groups vanish, you get the existence of these blended extensions for free. And the second result is that expand NL is canonically a torsor over X1, A3, A1. So extensions of X group of A3, extensions of A3 by A1. So blended extensions, isomorphism of blended extensions, a natural way, a torsor over this X1 group. Okay, so now I'm going to apply this to what we had. How are we doing time? Okay, so we have about, I'm running, I have maybe around 12 minutes or so, 11 minutes? Actually, no, around maybe 8 or 9 minutes. So I'm going to go a little faster. But so I'm going to take more of a logarithm here, more of zeta values here, and apply Grothendieck's theory. Because X2 groups all vanish for mixed state motives, I get existence of blended extensions. And then because X1 of 1 by Qn plus 1, when n is odd, X1 groups vanish, I actually get a unique motive up to isomorphism that fits in a blended extension like this. And then it's, so this would be a three-dimensional motive. Its associated derivative is isomorphic to the direct sum of these three. So that answers my first question about existence of three-dimensional, motive that has these two as the sub quotients. Now, look, I have the period matrix of this motive written here. So here you have the motive of zeta n. Here you have the motive of log p. And then there's a new entry here that we're going to come back to this entry in a couple of minutes. But okay, so that answers my first question. Now moving on to my second question. The second question was that, well, if there's such a motive, would the Grothendieck period conjecture for this motive imply the algebraic independence? Now, I'm going to make a definition here. I'm going to say that a motive has a maximal unipotent radical if it's the Lie algebra of its unipotent radical is actually equal to this W minus 1 n. Because remember, this was always contained in here. We say that it's maximal if it's actually equal to that. Now, a related notion is the notion of totally non-splitting for extensions, which is a strengthening of the notion of just non-splitting. So the definition is the following, that you would say an extension of x by y is totally non-split if, when you think about it as an extension of 1 by harm xy, by the canonical isomorphism, that extension doesn't come from any proper sub-object of this harm. Now, as long as when you're looking at extensions of 1 by x, if x is simple, then totally non-splitting would be the same as just non-splitting. But if x is not simple, then it becomes actually a stronger notion. Now, there's a connection between maximality, unipotent radicals, and this total non-splitting, and that's sort of summarized here, some aspects of it. if your motive has a maximal unipotent radical, then all the extensions that you could get from the weight filtration of the motive, all those extensions are totally non-split. And the converse is false in general. The total non-splitting of all of these doesn't imply maximality of the unipotent radical. However, if you only have two weights, then the converse is true. Total non-splitting is the same as maximal. And this two-weight case is due to work of Bertrand and Hardon. Well, separately. Bertrand does this for the setting of D modules, and Erdogan does this more generally.
In Payman, when you are telling that converse is false in general, are the specific example of
Absolutely. So by looking, you can make it three-dimensional example using one motifs, and it's actually easy to make that example. So three-dimensional one motive where all these extensions are total non-split, but the unipotent radical is not maximal. Actually, so I can. If you look at one of my papers, the one that was published, I think, in the Australian Bulletin of Australian Mathematical Society, there's an example there. It's easy to construct it.
So thank you.
No problem. Now, this theorem joined with Kumar that says the following, that suppose that X, and I'm emphasizing here that X is not necessarily a mixed Tate motive. So this is really much more general than that. Suppose that you've got a motive X that has exactly three weights, A1, A2, A3. So by that, I mean that when I look at the associated graded, it has three pieces, three different weights. And was that a question? Yeah. Okay, so now suppose the following two conditions. First condition is that the extension of GER2, sorry, is there a question? Mohammed Reza, I think you're cutting out. If you have a question, I can't hear you. I don't know if the problem's on.
No, actually, I had a connection. My connection just lag off. Sorry.
You know, no problem. I thought you had a question. But anyway, suppose that the two extensions that sort of the consecutive, extensions that you get from X. So one of them is, I'm looking at the successive graded pieces, and I get two extensions out of X. Suppose that those two extensions are both totally non-split. And suppose that when you look at the internal form of GER2 to comma GER1 and GER3 comma GER2, these two don't have any non-zero isomorphic sub-objects. Then X will have a maximal unipotent radical. So this is now what it's doing, as I said. So those total non-splittings are not enough by themselves. It's providing a sufficient condition under which the total non-splitting will actually be enough. Okay, but it's for a motive with exactly three weights. Now going back to our example, my second question back then. So we saw that there's these canonical motives with these two subquotients and this period matrix. Now these two things here are, well, this one would be just Q1, and then this one would be Qn. Well, they don't have any non-zero isomorphic sub-objects, so condition 2 is satisfied. These two are totally non-split, because they are non-split, and all of these are simple objects. So you're exactly in this situation, and what you get is that the unipotent radical of this motive is maximal. And so the Motivic Galois group will have dimension. So dimension of the reductive quotient, maximal reductive quotient is 1. And then because the unipotent radical is maximal, the unipotent radical is just this.
But pi and p is just notation?
Yes. Yeah. So it's this a new entry here. Yeah, it's just a notation, and it means this new entry here. So the Motivic Galois group will be 4-dimensional. Growing period conjecture says that transcendence degree of the period should be 4. And when I look at this period matrix, I get that actually pi zeta n log p, and this new number should be algebraically independent. And the open question is, well, what's this new number? And one comment I'll make about that is that it's actually a period. So this is a mixed state motive over, because of this log p, it's ramified at p. It's a mixed state motive over z adjoint 1 over p. And aside from, p being 2 and 3, there's not much known about, these categories. So, there's not even, we don't know anything about, in general about these periods. So the nature of this number is actually mysterious. So it'll be interesting to find this out. So I'm out of time, so I didn't actually get to, I made these slides and I thought that I'll go as far as I can in that. So I was going to talk about a more recent work, and I didn't get to it. That's it's okay. Maybe I'll give another talk and continue with this later
I
on.
think it's a good idea to give a whole new talk on this new part that you did.
Yeah, because it would be rushed anyway. So I'll just wait here. One comment I'll make is that, so this result that I stated here, this was, where is it? Yes, sorry. This was for motives with 3 weights. And this now, is generalized to motives with any number of weights. So it's a nice theory. The notion of blended extensions is generalized to motives with arbitrary number of weights. This result is generalized. So the whole thing, everything that I talked about is generalized to motives with arbitrary number of weights. I'll stop here.